In last class, we have seen the field distribution on the transmission line, and we found that transmission lines support transverse electric magnetic mode. What do you mean by transverse? Anything, any quantity or any plane which is perpendicular to the direction of propagation. What was the definition of transmission line? Transmission line guides the energy along its length. That this was the z direction. There was the field, electric field and magnetic field. They were perpendicular to the direction of propagation. So also you have seen there was a plane which is perpendicular to the direction of propagation, that was xy plane, and xy plane, E and H, these all three things are perpendicular to the direction of propagation, and we say it's a transverse. In this figure today we will study the transit time. In this figure, this is the length of the transmission line. Okay, I have drawn one wavelength. Remember that I have drawn one wave, and length of one cycle is known as wavelength. This transmission line is connected with excitation having frequency f, and this frequency is known as operating frequency, and with the help of equation c is equal to nu lambda, we can calculate lambda, and this lambda is known as operating wavelength. By inspecting this figure, I can say that the length of the transmission line is very greater than the operating wavelength. Okay, so I can also predict that this wave will take some time to reach at point B. Means from point A to B, it will when it travels, then it will take some time, and this time is known as transit time. With the help of this equation, this is the length, and it will move with some velocity, and velocity of this single wave is known as phase velocity. Remember that. Never ever say that this wave travel with the velocity of light. It will travel with it will travel with phase velocity, and that phase velocity will be always less than the velocity of the light. What is the reason behind it? Actually, we assume that these conductors are perfect, but in reality these conductors are not a perfect conductor. That's why the wave moves with less velocity as compared to the velocity of light. Okay, mathematicals, we give some mathematical support here. If this is the length of the transmission line, I can say length is very greater than lambda. Okay, how can we calculate lambda? From this equation, velocity is equal to frequency into lambda, then I can calculate the value of lambda, Vp over f. Put this value here and modify this equation. L over Vp is greater than, very greater than 1 over f, and that L over Vp is nothing but transit time. What is transit time? Time taken by the wave to reach at point B is known as transit time. Okay, what is this wave is periodic in nature. Time and do you time period? What is time period? Time period is nothing but it is the time after that wave repeats its shape, and this time is nothing but this is the time period of the wave. So 1 over f I can write it is capital T. So what is transit time effect? Transit time effect, finally we can say, in the transmission line from point A to B, wave will take some time, and this time is nothing but it's a transit time. There is another thing that happens in the higher frequency transmission line, that is skin effect. What is skin effect? Suppose that there is a conductor and we have applied DC. Look at the cross sectional area of this conductor, and I have filled with some color. It means that current will flow all the cross sectional area, in I should say in full cross sectional area. And there is a quantity, there is a property of conductor which opposes the flow of current, is known as resistance. And we have applied here DC, so there will be DC resistance. And in the second figure I have applied AC, and AC has some frequency. Look at the cross sectional area of this conductor. Okay, the current does not flow through all the region, it flows through some region. Okay, so can I say current is flowing in this area? Means I can say there is a reduction of the effective area. If effective area is reducing, then resistance will increase. Okay, let's take another thing. If I increase the frequency, then this effective area of the current, this effective area of the flow of the current is again reducing. Means whenever I increase the frequency, the effective area is reducing. Effective area is reducing, means resistance is increasing, and we say it's a AC resistance because we have applied AC. Okay, look at this figure. From this figure I can say current will be maximum at the skin of the conductor. Whenever I move in radial direction, current will reduce. Means I can say one more thing, this will be the high impedance zone and this will be the low impedance zone, because current always travel in lower resistance path. Okay, so this is the thickness where the current flows, and this thickness is known as skin depth. And skin depth depends on the frequency and of material property, and sigma is related with the property of the conductor. Okay, why does skin effect come in picture? Suppose that there is a conductor and current is flowing in upward direction. Because of current there will be a magnetic field which is in the form of closed loop. I have drawn another two loops here, and these loops are nothing but eddy currents. Eddy current always flow in the form of loop. Okay, they are opposite to each other. These loops are opposite to each other. Direction of flow of current, eddy current, are opposite to each other. They will cancel out to each other. Means there is no current at the central region. It means that the tendency of flow of electron will come in picture on the skin of the conductor. So remember that in the case of higher frequency, current flows through the skin of the conductor. And this is all about for today's lecture. In next lecture we will see what is lumped circuit or lumped parameter or distributed parameter. And apart from that we will also study the what is the primary constant of the transmission line. How does these parameters come in picture, we will also see. So thank you very much, and please watch my next lecture.